Welcome to today's webinar, a deeper dive into Apache MXNet on AWS. Our presenter today is Sunil Malya. Sunil is a solutions architect focused on deep learning at AWS, working with computers in various industry verticals. Prior to that, he co-founded the neuroscience and machine learning-based image analysis and video thumbnail recommendation company, Neon Labs. He's also worked on building large-scale, low-latency systems at Zynga and has an acute passion for serverless computing. Today we also have Dominic Divakaruni and Kurji Shu. They'll be our moderators today, answering your questions you put into the Q&A panel. Sunil, welcome. The floor is now yours.
Hello everyone, good afternoon. Here's the agenda for today. We're going to walk through a little bit of introduction to Apache MXNet. Then I'll walk you through how we can run distributed deep learning on AWS. We'll go through some deep learning basics, an overview of MXNet programming model, and then we'll get some hands-on to train our first neural network using MXNet. Deep learning has been solving multiple domain problems, and some of the domains like image understanding, speech recognition. For example, Alexa from Amazon uses deep learning to do ASR. Also do natural language processing, and autonomous driving is also being solved using deep learning. Some of the customers that use artificial intelligence on AWS are Netflix, FINRA, Pinterest. TuSimple here, one of AWS's customer, uses Apache MXNet to do autonomous driving. Our vision here at AWS is to use the expertise and lessons learned from Sorry for the feedback. So the lessons learned from our customers and thousands of engineers focused on AI at Amazon to put intelligence in the hands of many developers. We believe that AI should be available to everyone, irrespective of their level of technical skill or ability. So we've built 3 layers on top of the hardware layer here at AWS. So the top layer is the AI services, the middle layer is the AI platform, and we have AI engines as well. Today, we're going to focus on Apache MXNet. So MXNet is an open source project that recently got accepted to the Apache incubator. We here at AWS and Amazon have chosen Apache MXNet as our deep learning framework of choice. And the 3 main reasons why we chose were programmability, portability, and performance. MXNet has a wide array of languages that you can code in, like Python, C++, Scala, Julia, MATLAB, etc. So we can develop highly efficient models for mobile and IoT applications. So for example, a ResNet 1000-layer network is approximately about 4 gigs. And we have been able to run MXNet on a Raspberry Pi. Performance, we love scalability at AWS. And one of the reasons that we chose was how linear the scaling was when we did distributed deep learning. Distributed deep learning. We evaluated various frameworks and we took models. So ImageNet, for people who are familiar with this competition, it consists of around 1.2 million images to label in various different categories. Now, these models that are listed like AlexNet, ResNet, Inception are models that have won the competition every year. And we took them and we did distributed deep learning to see how we can scale with MXNet. And as you can see, we have been able to achieve 88% of the ideal efficiency speed up that we get by scaling across GPUs. We did that using 16 of the P2 16XL AWS instances. And this was done using a CloudFormation template with the deep learning AMI that AWS provides. The training setup, which is now made available through our deep learning CloudFormation template, it's actually on GitHub, and we have a blog post available as well. So essentially the architecture looks like this. We have auto-scaling groups for the worker nodes. There's a single master node that controls and distributes the task. And we'll walk through how we can set up this CloudFormation template. So we go to the CloudFormation service in the console. We now create a stack. We can choose the file that is on GitHub. You can download this. And once you select next, we can configure the instance type that we need. The G2 or the P2 instance, even CPU instances are available right now. And we can specify the number of workers that we want and give a stack name as well. Once that's done, you can feel free to name your instances and also optionally choose IAM role. Now, once you've hit that, if you go back to the CloudFormation stacks, we can get a list of the stacks and the progress that our current stack is going through. And this is happening inside the VPC of your account. Once we have had all the instances spin up, we can actually SSH into the master and see how it looks like. We will now kick off a distributed job that will run across the workers. As you can see, we are using the MNIST, train MNIST script here, and the training has started. So we know the master node also takes part in the computation. So we're going to just check if the workers are working. And as we switch across, the training is being distributed as illustrated in the outputs on the worker node. Now, training is finished. So as you saw, it was really simple to launch the job, a cluster, and scale up and down through the auto-scaling group there. Let's now walk through some of the basics of deep learning. So deep learning or neural nets actually were proposed in the mid-60s. And it was a loose inspiration on how we thought the neurons in the brain worked. So here's a biological neuron, which consists of a cell body and dendrites. So dendrites are appendages that listen to other neurons. Then, as you can see, there's an axon. The axon is a part that carries the impulse away from the cell body. So the cell body performs certain computation. So it receives multiple inputs from through the dendrites and sends an activation potential across the axon. And then it branches out to different axon terminals, which connect to various other neurons. So they're not physically connected, but it's connected through what we call a synapse. Remember, the brain is an electrical system. Now, we took this as a loose inspiration and tried to create something from a mathematical perspective. So as you see at the right-hand side of the slide, we see an input x0, which is an input from an axon of the neuron, gets into a synapse. The synapse has a weight, so we multiply the weight with the input, and then it gets into the cell body. The cell body has a lot of other neurons that it takes as input, and then performs a summation with a bias. And then once that's in there, it sends it through an activation function. Think of it as thresholding. I'll explain that in the next slides. And sends an output through the axon. So loosely speaking, in code, we can have a neuron tick defined as follows, where the cell body takes the sum of all the inputs and the weights, plus the bias, and the firing, which is the activation function that I defined, and it returns that rate. Let's do a deep dive on the artificial neuron. As I explained, it can have several inputs, and each connection has a weight. It could be different. And all these weights get into the output as the summation that I explained earlier. The output is a linear function of the inputs, which is the sigma wi xi. And now what we do is we actually send it through a non-linearity. So when we want to classify or train complex networks that we apply to nonlinear problems, we introduce this nonlinearity by sending it through a thresholding or an activation function. So typically sigmoid, tanh have been used to create the nonlinearity in the network. Now, the training process is essentially we are trying to learn the weights and the bias. So essentially we are trying to create that function which is going to either classify or identify the inputs to the desired output. Now, a neural network has three layers: the input layer, the hidden layer, and the output layer. So typically when the neural nets were proposed in the early 60s, they used to have a single layer. And as we started adding more layers, the network started getting deep. And that's where the word deep in deep neural networks come from, and deep learning as well. So and just to add, the optimal size, the depth of the layers is typically determined, experimentally, but in general, for the number of neurons in a given layer is between the size of the input and the output layers. Now, let's just walk through some illustration of what's happening in a deep neural network. So we have the input array, and there are weights that connect each of the neurons to the hidden layers, and the hidden layer 1 is connected to the hidden layer 2. In this case, they are fully connected. As you can see, every input is connected to every other input on the next layer. Now, we send the inputs through the first layer, and the weights are, we have various techniques to initialize the weights. They were typically random, but it's still an active area of research. So there have been several proposed, like Xavier initialization, to initialize these weights. So as we go through the network, we then compute the output. So we just went through a single input through the network. But say we actually didn't get the desired output, which in our case was X. Let's say we got X prime. Now, what the network does here is we actually send the error back through the network so that it can correct itself and find the right weights that is going to minimize the error in our network. Now, what it does is we take the entire matrix in this case, and we're computing the delta for each of those weights, and that happens through a process called gradient descent. And we propagate that all the way through the network, and this happens for every input into the network, and we can do that several times until we get an error that is acceptable for our network. Now, if we go a little deeper into what these layers are learning, they tend to learn hierarchical features. So in this case of face examples, as you can see, the layer 1 seems to be actually learning some of the edges, and by layer 2 it's actually learning certain features that form a face. As you can see, there's eyes, there's ears, nose, etc. And through the layers, layer 3, it actually tries and recognizes certain kinds of faces. So this is just a representation of what your network is learning. Now let's dig a little into the programming model that MXNet has to offer. If we look at imperative programming, say in Python, right, where things get evaluated immediately. So as you say, a equal to np.1 of 10, it is actually evaluated right there. So it's straightforward, it's flexible. We can actually write loops and conditions. It's just like programming languages that we're really used to. Now, the next is a declarative program where we are defining things. A great example which developers may be familiar is SQL. They tend to define a query, and the engine takes care of optimizing that. So that's the declarative programming paradigm. So it uses, you can actually define matrices or multiplication or your variables in this case, and they can be evaluated lazily, which allows us to do a lot of memory optimization and compute optimization as well. But it's certainly less flexible than imperative programming. Now, what MXNet has is a mixed programming paradigm. It brings the power of both imperative and declarative and combines them so that you can actually use the power of both paradigms. So you can declare your network symbolically, which you can see at the bottom half, but at the same time you can define iterators and pre-processing and all of that in the imperative language. So it becomes really easy and compact to define things, but also use the power of imperative language, say like Python, to build efficient networks. Now, let's actually go and build our first model to classify handwritten digits. Now, just a little background. So the MNIST dataset consists of handwritten digits, and we have a single grayscale channel, and these images have been resized to 28 by 28. So as we execute the first cell, essentially it's downloading the data set. And let's just visualize the data set. So our data set, as you can see, those are handwritten digits, it's grayscale image, and it's labeled. What we do next is we create the data iterators. So essentially, these images, we will shape them into 4D matrices. So as you can see here, we are initializing them with, so the shape is batch size, the number of channels. In this case, it's going to be 1, the width and height, 28 by 28. So we are iterating through the ND array. So MXNet has various operators. In this case, we are going to use ND iterator or the NumPy that is defined NumPy arrays that we got as our input. So we create two iterators. One is a training iterator and the other one's a validation iterator. And in this case, we have chosen the batch size to be 100. There are other iterators available with MXNet as well. So you can take various images and convert them to a binary format with indexes and give it as an iterator, which then MXNet can actually take and distribute across different GPUs or instances to make the training simpler. So the first case we're going to do is use a multi-layer perceptron. And this is an older concept. It's one of the first concepts that came out when neural networks were proposed in the mid-60s. So a multi-layer perceptron has several fully connected layers, which is similar to a network that I illustrated earlier. So the layer has two parameters, m into x, and it is computing the output with, the output function is wx by b. So w is the weight matrix, x is the input, and b is the bias. Each of the fully connected layer is fed to the activation layer. So we will send them through a sigmoid function or a tanh function. But there was another activation function which was proposed around 2010, which is called RealmU, which is essentially a thresholding function, thresholded at 0, where any value that is less than 0 gets thresholded to 0, and it monotonically increases for any value that is greater than 0. Now, all the network and the diagrams may have seemed complicated, but to actually write the model, it's really easy. As you can see, it's around 10 to 12 lines of code here. And that is the power of the declarative language paradigm that I talked about. We first define a data variable, and then our data is actually flattened because of the shape that we formed earlier. We then have our first fully connected layer, and we have 128 nodes. And then it goes through an activation function, which is then fed to the next fully connected layer, goes through the activation function, and then we have a fully connected layer at the end, which is then fed to a Softmax classifier. So if you remember, our objective here is to classify digits from 0 to 9. Hence you see the number of nodes at the end is 10. And we use Softmax to give us the probabilities of each, is this digit a 0, is this digit a 1, or and so on. So let's execute that. And what we do is we plot and visualize the network. As you can see, the data is 1 into 28 into 28, and then goes through fully connected layer, RealmU, and finally into a Softmax output. And remember the fully connected layer, which is the 10, and this is usually equal to the number of outputs that we desire, or the classes, in this case 0 to 9. Now we start training the model. So as you see here, we first define the feed forward, and then we do a model.fit. The feed forward phase, if you remember, is when the inputs go through the layers and the network to the output. We see here we give batches. Our batch size is 100. We defined a callback function so that we get an idea every 200 batch size, every 200 samples, we get an idea of to where and how the network is training. As you can see, the training accuracy keeps increasing as we feed it more inputs. And finally, remember that we actually kept a validation set, the validation iterator, and this is helpful to kind of test the network on actually samples that it didn't see during the training phase. Now let's look at, we'll pick one at random and see how good we were able to predict. So in this case, we were trying to predict a 7, and our network has classified it as a 7 with 98.86% accuracy. It's not bad. Now, since this is a notebook, we can actually embed HTML code, which is really useful. As you can see in this case, what we'll try and do is I'm going to actually try and draw a digit and get our model to classify. As you can see, it has an error rate. So the 7 is a little weirdly shaped. It could be, remember the network is only as good as the data we actually fed. So let's try a 3. It seems to classify as 3. That's a good thing. Let's try and figure out if we can classify a 0. So as you can see, we don't get really good results here, and that's because we are using a really simple network called the perceptron, multilayer perceptron here, and also the MNIST dataset is quite sparse. So ideally, when we do deep learning, we need to define a really good, robust network. The other thing is you need lots and lots of data. And just to be clear, let's draw. To the humans, this may look like a 7, but note that it is off the center. So if you look at the training data up here, everything was centered. So my guess is the network here is going to classify this as a 7 and not a 1. As you can see, because for the most part, that is where the edges are present in the image in our inputs. So what would be a more robust network? So enter convolutional neural networks. So these are state-of-the-art neural networks that are used for facial analysis, object detection, and remember those ImageNet competition that I described? Most of them are convolutional neural networks. Now we take the input matrix here and take a convolution kernel and actually run it through the inputs. And the output that we get is then piped to the next layer and so on. And we can have multiple number of these filters. So again, let's look at the declaration here. So we pick a kernel size of 5,5 and add 20 filters. I'm going to just execute this so that we can actually visualize this while I describe the network. And at each step, since we are actually running it through a kernel, the input size reduces. So if we started by a 20 by 28 by 28 matrix, as you see, it gets down to a 24 by 24 matrix. And number 20 here is the number of filters that we ran, we actually ran through at that layer. And that continues but through an activation function. But enter, we have a new layer here. It's called a max pooling layer. Essentially, a max pooling layer is reducing the size of the input. So these matrices can get really large, and we may not need the entire image. So it's essentially subsampling the image. So what it does is in this matrix, as you can see, it takes 2 by 2 and picks the max of the pixel value here. For your example, on the left quadrant, so to speak, we have max of 7, and then a 9 over here, and so on. So we keep reducing the size so that it's easier for us to compute. So back to the declaration, we have a convolution layer, and then we send it through an activation function. In this case, it's a tanh, and then goes through a pooling layer. So we have 2 convolution layers, and the third is we have a fully connected layer. And then finally, we have, for the output, we have a fully connected layer with a Softmax classifier. And this is one of the earliest CNNs that was proposed by Jan LeCun. It's called the LINET. And in this case, earlier, as you saw, even though our training was fast, it was really simple. It was trained using only a CPU. In this case, we are actually going to use GPU for training because as you can see, we're doing more complicated analysis or multiplications in this case. And similarly to the last time, we do have outputs for every 200 bats, and we are getting better accuracy than we did the last time. And it is completed, and we can reuse the cell here, given that's the same notebook, and you can just test. Now it was able to classify it better. So CNNs tend to be more robust than the earlier perceptron models. Now, to give you guys an overview of the MXNet project. So as I mentioned earlier, it's actually an open source project currently in the Apache incubator. It was founded by a bunch of research scientists out of the University of Washington and Carnegie Mellon. It's got multi-language support. It's got state-of-the-art model support like CNNs, the one we saw, LSTMs, and RNNs. The notebooks that I showed the example are available on GitHub. We have tutorials that go through some of the basic concepts. There are applications, and we have pre-trained models that you could use to either extend or deploy in production. We also have a lot of resources through blog posts and GitHub and videos that teach you on how you can get started on MXNet. We also have developer resources for the deep learning AMI that we used in our CloudFormation template. It is available in Amazon Linux and Ubuntu as well. We also have tutorials and links on how you can run predictions on Lambda using MXNet, also ECS and Docker. As I mentioned earlier, we also have Raspberry Pi tutorial on how you can get MXNet up and running, deploy a model, and it actually detects, classifies wine. That's the end of the presentation. I'll switch to questions.